Okay, so right now we're going to solve one beam problem, beam deflection, using Castigliano. Castiglianos. So let's say we have a beam here, and the beam is fixed in the wall, and there is a support here, and there is a force applied 10K here, and there is a moment applied right here. M is equal to 4K Newton meter. That's Newton, right? This distance is 1 meter, and this is 2 meters, and from here to here is also 2 meters. And take EI to be 1, modulo of elasticity time moment of error, moment of inertia is unit, just to make the calculation simple. So now the question is, find the deflection at point. So let's use another color. Let's say this is A and B, C, D. The question is, find V at D, the vertical deflection at point D, using Castigliano theorem. So that's the question, okay? So, before I do this, I go to the Castigliano theorem. I say the deflection using Castigliano theorem at a point was the derivative of the internal energy of the entire system. This is U by total, the internal energy, with respect to a force acting on that point, and this is the deflection along the direction of the acting force. So here I don't have a force P. I only have a force 10K, right? So in order to get this trick working, you need to make this, instead of 10K, just let's say this is P, right? So assume that the force applied here is not fixed to 10K. It's P. And then once we do all this thing, after we do derivative and everything, evaluate it at P is equal to 10K. That gives you the numerical value for 10K deflection at this point. Now if you want to find the deflection right here, then you put another force P here, so that's going to be 10K, don't touch it. Here put another force P, do all this calculation, and at the end you say P 0, because we didn't have force here, right? P was 0, but we have a 10K here. So it's based on you how you can add that force P. There is a lot of ways to do that. So here I'll just say P arbitrarily, and then after I do calculation I'll evaluate at 10K. So this is Castigliano theorem, right? So if I want to go ahead, I can write this like partial P. And what's the internal energy of the beam? Well, as you can remember it, in the class, we took an element in the beam that has some d theta deflection, and we said 1/2 md theta is d ui, the infinitesimal internal energy or strength energy stored in this element. Now if you integrate this over the entire beam, it's going to be a total theta from 0 to L, the entire beam. 1/2 m, and we know that d theta is equal to m over ei dx, right? This was, we proved this using radius of curvature. So if you put it back here, then we get integral from 0 to L 1 over 2 m, hold on, I already have it here, integral, this integral of this, so integral 0 to m, 1 over 2 m, now I should put d theta, instead of d theta, I put m over ei dx, this is simply d theta, m, 1 over 2, and then add all this infinitesimal energy stored in tiny slices, right, to get the total energy. So that's going to be, take 1 over 2 out, that's going to be 1 over 2 integral m squared over ei dx, right? So I took this out of integral because it's constant, integral 0 to L m squared ei dx. So this is my ui that I should use here, internal energy in the entire beam. So I just put it here. So you say, instead of ui, I do partial p times, inside this, 1 over 2 integral 0 to L m squared ei dx. So that's it, right? But look, here, ei is not a function of p, right? 1 over 2 is not a function of p. ei is not a function of p. But the moment is a function of x and also is a function of p. If this is p, right, the moment everywhere in this cross section is also a function of that load. So if I take this derivative inside this integral, then I should take derivative of this using chain rule. And that's going to be, so you take this here, integral, the derivative with respect to p m2 over ei dx from 0 to m. Right? So you take this derivative p of this term, because this moment is a function of p. Right? The rest is just the same. Now, what is, if you have function fx, this is just a review of chain rule in calculus. The derivative, and if this function is a function of g, x, the derivative of this with respect to x is the derivative of f with respect to g times derivative of g with respect to x. This was in the basic calculus 1. Now we do the same thing. The derivative of moment squared with respect to p is the derivative of moment with respect to m times derivative of moment with respect to p. So that's going to give you 1 over 2 integral 0 to L 2m, the derivative of this with respect to m, times derivative of moment with respect to p. This is equal to this term using chain rule, divided by ei dx. Right? Now these two cancel out with these two, so at the end, and also this ei is 1, right? ei is 1. So this is just 1. So you get integral 0 to L m partial p dx. That's going to be the deflection at point D, where force P is acting. So keep this formula. So what do I need to do? All I need to do is to find moment, right? If I have the moment relation, then I can take derivative with respect to P, so that's going to be a simple term. Then if I take one integral, I'm going to find deflection D. There is no double integration, there is no area calculation, and there is no boundary condition. That's just amazing. So let's do that. Let's keep this relation here. So if I write it here, that relation, let's write it delta. Let's get a better color. let's write it here. Delta at B is equal to integral from 0 to L M partial P dx. This formula that we derived. Now, because we don't have enough space, I'm going to erase the rest of it and start solving it using that formula. So you want to find the moment relation. Again, you have several different ways to do that. I use Heaviside, right? So here at A, you have AX, AY, and MA. And then here you have C. You know what? This becomes statically indeterminate because CY, one variable unknown, 2, 3, 4. 4 unknown. So the moment diagram that we find is going to be statically indeterminate, but it's okay, right? Although we don't get a numerical number, there is going to be one variable at the end showing up in the relation, but it's okay, right? So just know that. So AX, AY, MA, C, Y, and then there is 2 external load, and this is just P, right? At the end, we say P is equal to 10K. So the energy of this, all we need is a moment diagram. So I'm going to write the equation, summation of force in X 0, that would give me AX. There is no other force in X is equal to 0. Summation of force in Y is equal to 0. That would give me AY plus CY minus P is equal to 0. You see, this is not 10K, this is just P. At the end, it becomes 10K. And then summation of moment around A is going to be 0. And that's going to give you MA by MA plus CY times 2 minus P times 4 is equal to 0. So, at the end, you get, this is 0, so you get AY is equal to P minus CY so for AY, one equation, one unknown. AY is equal to P minus CY. Look, we can't solve for CY because this 4 unknown, 3 equations. So one remains as a parameter, CY. And also we have another parameter, P, because this we needed to take derivative in Castiglianos. But don't worry about it. At the end, we get a relation. So here, for MA, if I solve for MA, then MA is going to be 4P minus 2CY. 4P minus 2CY. So this is MA, and this is AX. So all I do, I'll just write it. AX is equal to 0. I'll just remove it because there is no force here. Now AY is equal to P minus CY. Let's write it like this. AY is equal to P minus CY. And this is AY at here. And MA is equal to 4P minus 2CY. That's MA. Now, again, I have to erase this in order to have enough space. Now, I'll go ahead and cut it from somewhere here. And this is my X. To write my moment relation. markers right down. So if you cut it here, you have a moment mx and the shear force coming down positive Vx and no axial force. So summation of moment around this point is mx for this system, right? Is mx minus cy times x minus 2 heavy side plus 4k, right, times x minus 1 heavy side power 0, right, negative ay, which is p minus cy times x plus ma. ma is 4p minus 2cy is equal to 0. So all I did, I considered the left, you could consider the right. In that case, if x is from right, just cut it from here, okay? And then you include all these things. You don't even need to consider reaction. But still, you have one cy, which is coming from indeterminate system, the nature of indeterminacy. You can't solve for this. And in fact, all this thing, the deflection, give us information that deflection at c is 0. Deflection at this point is 0, the slope at this point is 0. So it gives us one equation that we need to solve. So we add it to the static equation in order to make the system determinate. So here, this is equal to 0. So this is moment m, this moment coming from cy times this distance. And this distance is heavy side minus 2, x minus 2 heavy side. Because if you are at before this term is not here, it's 0. Then we go to this guy, and this 4k, x minus 1 heavy side to power 0, not 1, it's power 1. Because it acts like a switch. If you are before that, there is no 4k. After that, there is just 4k. There is no x minus 1 times 4k. Right? And then negative ay, this is ay. Time x. Then plus, this is wall moment, which is 4, this is ma. Right? Wall moment. Right? Is equal to 0. So mx, all I need here, I need mx multiplied by the derivative of mx with respect to p, not x with respect to p. So my mx, the first iteration I need is this. Take everything right, cy times x minus 2, 1 plus negative 4k times x minus 1, 0 plus p minus cy times x plus 2cy minus 4p. So this relation, take everything right, cy x minus 2 minus 4k x minus 0 plus p minus cy x plus 2cy minus 4p. So this is this term. I need to put it in Castiglianos. Now how about this term? So you take the derivative of m x with respect to p. That's what you do. So this becomes, do you have a p term here? No. So the derivative of this term is 0 plus the derivative of this term is 0. Right? Now what is the derivative of this term? So this is px minus cyx. Right? So the coefficient of p is x. So there is a derivative with respect to px. But the term that say negative cyx, that derivative is 0 because there is no p there. Right? And then derivative 0, there is no p here. There is a p here. X negative 4. The negative 4 is coefficient of p here. So the second term is even simpler than the first term. So that's the reason Castigliano give you a simpler integral compared to energy, original energy. Original energy, you have integral m squared over 2ei. It's internal energy. Right? You have to compute that this integral is complicated than that. Second advantage is you have to equal this to external work we do on the system to move it. Right here we don't do external computation, external work computation. So we only have the derivative at this point is equal to the deflection. So my deflection is equal to integral at the integral from 0.
Oh, I thought you were
I'm actually teaching, doing some online class. Yeah, it's okay. Right. So it's integral from 0 to L of this integral at D, deflection D is integral from 0 to L. This term, Cy x minus 2 minus 4k x minus 1, 0, plus p minus cy x plus 2cy minus 4p. This m times the derivative with respect to p, x minus 4 times dx. Now here, if you note, this integral, I have two unknown, cy and p. Right? Everything else is just, this L is simply from here to here, which is 4 meters. And then we have a bunch of x, which after we take the integral, they're going to go away. Right? And then at the end, what I get out of this integral, if I evaluate it correctly, I get something, a function of cy and p. Now what is the value of p? At the end, you put p is equal to 10k. You just make it variable to take this integral, to take all this derivative. You just artificially make it variable. But at the end, you put p is 10k. So the end result is a function of cy, right? So you get deflection after you take this integral. We will talk, this integral is very easy to take. So you say that this integral from 0 to 4 is integral from 0 to 1, and then you simplify this between 0 and 1. Right now we don't have enough space. So if this is between 0 and 1, this term is not there, this term is not there because the argument is negative. This term is there, this term is there, this term is there. So it's going to be this term times x minus 4 plus integral from 1 to 2. So you basically go interval based because this function is a very complicated. It's piecewise continuous function. You can't just think like a line and take an integral. So then you go from this point to this point, 1 to 2. 1 to 2, this term is right there. So that's going to be negative 4k times x minus 1 to power 0, which is just negative 4k. So you have negative 4k here. This term is not there. You are before 2. So this is 0. This term is there. This term is there. This term. So it's negative 4k plus this times x minus 4 from 1 to 2. And then you say plus from 2 to 4. This entire integral. Between 2 and 4, you have all of them. You have cy x minus 2, negative 4k, times this is just simply negative 4k, plus py minus cy times x plus times x minus 1. So this integral, this is going to convert itself to 3 integrals. But they are just simple integrals. You can also put this in calculator and evaluate it. So at the end, what you get is a function. This gives you the deflection is a function at D is something, some numbers times cy plus another number, a linear relation. That's what you get at the end. and you calculate this integral. Now, in this case, we don't have a condition at point B. Now, if we could apply P at point C, then the same mechanism, exactly the same mechanism, will give you deflection at point C is equal to something times Cy plus something else. This is something else. Now, if you use this relation, what is the deflection at point C? The deflection is 0. So that's going to give you, we call it compatibility relation, extra equation that you can solve to make the system determinate. So we have 3 equations for moment x, summation of force in x0, y0, moment around endpoint 0. And the force equation is this. Deflection here is 0. So I have 4 equations, 4 unknown. Ax, Ay, Cy, and Ma. Then I can solve everything. It becomes determinate. It's not statically determinate, but it becomes determinate. So this is just, I want to show you how you do this. And we will solve one example after this to cover the frames or truss. We can do the same exact. All you need to do is compute the energy function for a frame or truss. And everything is going to be exactly the same.